Okay, then let's start with gravitation, chapter 7. Chapter 7 of class 11 physics, gravitation. The topics in this chapter are Kepler's laws, universe's law of gravitation, the gravitational constant, acceleration due to gravity of the earth, acceleration due to gravity below and above the surface of earth, gravitational potential energy, escape speed, earth satellites, energy of an orbiting satellite, summary points to ponder exercises. First, let's start off with introduction. Early in our lives, we become aware of the tendency of all material objects to be attracted towards the earth. Anything thrown up falls down and towards the earth. Going uphill is lot more tiring than going downhill. Raindrops from the clouds above fall towards the earth, and there are many other such phenomena. Historically, it was Italian physicist Galileo (1564 to 1642) who recognized the fact that all bodies, irrespective of their masses, are accelerated towards the earth with a constant acceleration. It is said that he made a public demonstration of this fact. To find the truth, he certainly did experiment with bodies rolling down inclined planes and arrived at a value of acceleration due to gravity which is close to more accurate value obtained later. A seemingly unrelated phenomena, observation of stars, planets, and their motion has been the subject of attention in many countries since the earliest of times. Observations since early times recognize stars which appeared in the sky with positions unchanged year after year. The more interesting objects are the planets which seem to have regular motions against the background of the stars. The earliest recorded model for planetary motions proposed by Ptolemy about 2000 years ago was a geocentric model in which all celestial objects, stars, the sun, and the planets all revolve around the earth. The only motion that was thought to be possible for celestial objects was motion in a circle. Complicated schemes of motion were put forward by Ptolemy in order to describe the observed motion of the planets. The planets were described as moving in circles, with the center of the circles themselves moving in larger circles. Similar theories were also advanced by Indian astronomers some 400 years later. However, a more elegant model in which the Sun was the center around which the planets revolved, the heliocentric model, was already mentioned by Aryabhatta 15th century AD in his treatise. 1,000 years later, a Polish monk named Nicolaus Copernicus 1473 to 1543 proposed a definitive model in which the planets moved in circles around a fixed central sun. His theory was discredited by the church, but notable amongst its supporters was Galileo, who had to face prosecution from the state for his beliefs. It was around the same time as Galileo, a nobleman called Tycho Brahe (1546 to 1601), hailing from Denmark, spent his entire lifetime recording observations of the planets with the naked eye. His compiled data were analyzed later by his assistant Johannes Kepler (1571 to 1640). 1571 to 1640, he could extract from the data three elegant laws that now go by the name of Kepler's laws. These laws were known to Newton and enabled him to make a great scientific leap in proposing his universal law of gravitation. Now, the first topic, that is Kepler's law. The three laws of Kepler can be stated as follows. First law, law of orbits. All planets move in elliptical orbits with the sun situated at one of the foci of the ellipse. This is the sun. These are the two focus, and sun is at the focus, where planets are revolving around like this in an elliptical pathway. This is the first law. An ellipse traced out by a planet around the sun, the closest point P is, and the farthest point is A. P is called the perihelion and A the aphelion. The semi-major axis is half the distance of AP. Okay. This point is called as perihelion, and this is aphelion. This is the closest point to the sun, farthest point to the sun. All the planets move in elliptical orbitals with the sun situated at one of the foci of the ellipse. This law was a deviation from the Copernican model, which allowed only circular orbits. The ellipse, of which the circle is a special case, is a closed curve which can be drawn very simply as follows. Select 2 points. This is how to draw an ellipse. Select 2 points F1, F2. Take a length of a string and fix its ends at F1 and F2 by pins. With the tip of the pencil, stretch the string, taut, and then draw a curve by moving the pencil, keeping the string taut throughout. This is how you draw an ellipse. The closed curve you get is called an ellipse. Clearly, for any point at any point t on the ellipse, the sum of the distances from f1 and f2 is a constant. Any point t, any point on the ellipse, any point here, here, or here, when we take the sum of these points, if this was a0, f1, or this is a, f1, and b, then a f1 plus b f1 will always be a constant, because we took a constant string there. This string will always remain constant. Wait, this is a wrong diagram. This is AF1 plus AF2, which is always a constant, or any other point T, TF1 plus TF2, this will also be a constant, meaning this both will be equal. These both are constant and they will also be equal. F1 and F2 are called the foci. Join the points F1 and F2 and extend the line to intersect the ellipse at point P and A as shown in figure 7.1. Okay, we are drawing the semi-major and semi-major axis. The midpoint of the line PA is the center of the ellipse O, and the length of PO equals AO. PO is equals to AO. That's why we took it as 2A here. This is A, this is A, this is B, this is B. AO is called the semi-major axis of the ellipse. AO is this one. AO is called the semi-major axis of the ellipse. For a circle, the two foci merge into one and semi-major axis becomes the radius of the circle. Next, second law of Kepler. Second law, law of areas. The line that joins any planet to the sun sweeps equal areas in equal intervals of time. This law comes from the observations that planets appear to move slower when they are farther from the sun than when they are near. Okay, the line that joins any planet to the sun, if this was a sun, this was a planet, this there is a line joining it, and it will cover equal distances, no, equal areas, it will sweep equal areas in equal amounts of time. The line that joins any planet to the sun sweeps equal areas, covers equal areas in equal intervals of time. This law comes from the observations that planets appear to move slower when they are farther from the sun than when they are near. When they are farther, they need to cover a lot of uh, they can cover a lot of area with a little distance, but when they are near, they need to cover a lot of distance to cover equal amount of area like this. The planet P moves around the sun in an elliptical orbit. The shaded area is the area delta A swept out in a small interval of time delta t. The third law is that law of periods. The square of the time period of a revolution of a planet is proportional to the cube of the semi-major axis of the ellipse traced out by the planet. T square will directly proportional to r cube, where t is the time period taken for a one complete revolution and r is the semi-major axis, basically this one. The third law states that the square of the time period is directly proportional to the cube of the magnitude of the semi-major axis. Table 7.1, which you see, gives the approximate time periods of revolution of 8 planets around the sun along with the values of their semi-major axis. Where A is the semi-major axis in units of 10 part 10 meter, T time period of revolution of the planet in years, Q quotient in units. A is the distance. Mercury, it is 5 into 10, 5.79 into 10 power 10 meters. And just with Neptune having the longest semi-major axis and time period, also Neptune having the longest time period, and most of the planets having a similar close quotient close to 3, with Jupiter having the highest. Okay, then the law of areas can be understood as a consequence of conservation of angular momentum, which is valid for any central force. Okay, why these planets sweep equal areas in equal interval of time is due to conservation of angular momentum. This is applicable for any kind of force. A central force is such that the force on the planet, the central force is such that the force on the planet is along the vector joining the sun and the planet. Okay, the central force is that the force acting on a planet is along the vector joining the sun and the planet. Let the sun be at the origin and let the position and momentum of the planet be denoted by r and p respectively. Then the area swept out by the planet of mass m in time interval delta t, delta A is given by half r v delta t. The area swept is given by half of r times where the position vector cross velocity vector. Hence, delta A by delta t, which is equals to r cross p by m. We just multiplied m and divided by m. We will get half r cross p by m and half r cross p, which is equal to L. L is angular momentum by 2m. Where v is the velocity, L is the angular momentum equal to r cross p. R cross p gives us the angular momentum. Okay, the formula is the amount of area covered. The formula will be delta A, which is equals to half of r cross v delta t, and the rate of area covered, which is given by this one, this formula is just sending it this side, and r cross v can be written as p by m. So half r cross p by m, and r cross p formula is L. Finally, we will get it as L by 2m. For a central force which is directed along r, L is a constant as the planet goes around. Hence, delta A by delta t is a constant according to the last equation. Okay. L is a constant for a planet as it goes around. And because of that, delta A by delta t, which is also constant. This is proving the law, that is, it will cover equal area, it will sweep equal area in equal amount of time. The law of areas, gravitation is the central force, and hence the law of areas follows. Example 7.1. Let the speed of planet at the perihelion closest to the sun p be vp, and the sun planet distant sp be rp. Relate rp and vp to the corresponding quantities at the epihelion ra and va. Will the planet take equal times to traverse BAC and CPB? BAC is this one, CPB is this one. Yes, it will take equal time because it is equal area. or it is not maybe, because we need to only consider this much area here. Let's see the solution. Answer: the magnitude of the angular momentum P, which is equals at P, is LP, which is equals to MP, RP and VP. Since inspection tells us that RP and VP are mutually perpendicular, similarly LA, MPRA and VA from angular momentum both are constant. Angular momentum will remain constant at both points. Because of that, we equate them. Mass will remain constant. Now we'll get the equation Vp by Va, which is equals to Rp by Ra by Rp. Velocity is inversely proportional to position here. And the formula of L which is equals to mvr, or mv, if we write it as p, that is a linear momentum, we'll get it is Rp. The same formula has been substituted here at two different points of the ellipse. The area SBAC bounded by the ellipse and the radius vector SB and SC is larger than SBPC in figure 7.1 from Kepler's second law. Equal areas are swept in equal amount of time. Hence, the pennant will take longer time to traverse BAC than CPB. As I said, if we consider in this diagram BAC, this is the area, and if we consider this is the area, and if we consider this area is larger than this area is larger, lesser. So according to Kepler's law, this area will take more time to cover because the area per unit time will remain constant. The larger the area, the larger the time taken. The smaller the area, the smaller the time taken. So it will not take equal times to cover this both. This will be longer, this will be lesser. Okay, then let's go to the next main topic, that is universal law of gravitation. Legend has it that observing an apple falling from a tree, Newton was inspired to arrive at an universal law of gravitation that led to an explanation of terrestrial gravitation as well as of Kepler's laws. Newton's reasoning was that the moon revolving in an orbit of radius Rm was subject to a centripetal acceleration due to Earth's gravity of magnitude. Any object that moves in a circular motion, it only moves in circular motion because there is centripetal force acting towards the center of its circular motion. If there was no circular centripetal force acting on it, there was no way the object was moving in circular motion. And hence, when Newton observed that the moon was revolving around the earth in a circular motion, he thought that there was a centripetal force acting towards the center, that is towards the earth, and he thought that it was nothing but the gravity of the earth pulling the moon towards its center, towards itself, that is providing and acting as a centripetal force. Centripetal acceleration due to Earth's gravity of magnitude. And he said that am, which is equals to v square by the radius, this is the basic formula of centripetal acceleration, v square by m, or omega square r. This is the centripetal acceleration formula. And in terms of writing it as a linear velocity, we can write it as we know that v equals omega r, and omega, which is equals to v by r. So v square by r square times r cancel, we'll get a, which is equals to v square by rm. And Okay, the formula was A centripetal, which is equals to V square by R, and since we know V, which is equals to 2 pi R by T, this is the formula for V, 2 pi R by T, formula for V of the moon. Then we can write A centripetal, which is equals to 2 pi R by T into 1 by R, this whole square, because we had a square. This we can write as 4 pi square R square by T square into 1 by R square get cancelled, and finally we'll get the equation ASC, which is equals to 4 pi R by 4 pi square R by T square, where R is the radius of the moon's circular orbit, T is the time period for one revolution, centripetal acceleration, pi square value we know, pi value we know, and substituting values we should get some value. Answer. Okay, that's how we got this value, where v is the speed of the moon related to the time period t by the relation 2 pi rm by t. The time period t is about 27.3 days, approximately 30 days we consider it, but here they took it as 27.3 days, and rm, that is already known, then to be about 3.84 into 10 power 8 meters. If we substitute these numbers in equation 7.3, we get a value that is acceleration of the moon towards the center much smaller than the value of acceleration due to gravity on the surface of the earth, arising also due to earth's gravitational attraction. This clearly shows that the force due to earth's gravity decreases with distance. If one assumes that gravitational force due to the earth decreases in proportion to inverse square of the distance from the center of the earth, we will have am is to am, that is the acceleration of the moon, directly proportional to inverse square of the radius of the moon, that is the gravitational acceleration due to gravity, is directly inversely directly proportional to the inverse square of the radius of the moon or earth. Okay, this is acceleration due to gravity, and this is the centripetal acceleration of the moon, and we get that g by am, which is approximately equal to 3600. In agreement with a value of g, in agreement with a value of g, which is approximately 9.8, and the value of am from equation 7.3, the observations led Newton to propose the following universal law of gravitation. Every body in the universe attracts every other body with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. This is the law, the gravitational law, universal gravitational law. The quotation is essentially from Newton's famous treatise called Mathematical Principles of Natural Philosophy. Principia for short. Stated mathematically, Newton's gravitational law leads the force F on a point mass m2 due to another point mass m1 has the magnitude of the forces, which is g m1 m2 by r square. This is the most famous law, the most known law here, given here, one of the most known laws. Equation 7.5 can be expressed in a vector form as f, which is equals to minus gm1 m2 by r square r cap, or minus gm1 m2 by r vector by m1 m2 by r cube times r vector. That should be an r vector, where g is the universal gravitational constant, r cap is the unit vector from m1 to m2, and r, which is equals to r2 minus r1, as shown in the figure. These are position vectors. R1 and R2 are position vectors. R is the m1 m2 vector. Gravitational force on m1 due to m2 is along r, where the vector r is r2 minus r1 vectors. The gravitational force will always be attractive, that is, the force F is along minus r. The force on point mass m due to m2 is, of course, minus F by the Newton's third law. That is, the forces will be equal and opposite. Thus, the gravitational force F12 on the body 1 due to 2 and F21 on the body 2 due to 1 are related as F12, which is equals to minus of F21. Magnitudes will be exactly same, but directions will be opposite. Before we can apply equation 7.5 to objects under consideration, we have to be very careful, since the law refers to point masses, whereas we deal with extended objects with having finite size. If you have a collection of point masses, the force on any one of them is the vector sum of gravitational forces exerted by the other point masses, as shown. This is if we have a collection of point masses, the force on any one of them is the vector sum of gravitational force exerted by the other point masses. Like example here, example is if there is a point mass here m1, and there are many point masses here m2, m3, m4, then the gravitational force will be in this direction. This is, let's assume, an position vector. This is r2, r3, and r4. The forces will be acting in this direction, in this direction, and in this direction. Now let's name them as f12, f14, and f13. Now for the total net force, F net on m1 on mass 1, which is equals to F12 vector vectorial sum of all the individual forces, F12 plus F13 plus F14. When we all add all of them individually, that is vectorially, we will get the value. We will get the forces value. That is a superposition theorem basically. Anyways, let's go back. This is the point here, m1, three masses here, where they just get vectorially added up. Gravitational force on a point mass is a vector sum of gravitational forces exerted by m2, m3 and m4. The total force on m1 is the vectorial sum. Okay, let's see the example here. Three equal masses of m kg, some mass m kg, each are fixed at the vertices of an equilateral triangle ABC. What is the force acting on the mass 2m placed at the centroid G of the triangle? That's the first sub question. What is the force if the mass at the vertex A is doubled? All the masses are same, that is 1m. This is the equilateral triangle. All angles are 60 degrees. The angle, first we need to find the force acting on mass 2m placed at the centroid. The angle between GC and position axis is 30 degree, and so is the angle between GB and the negative axis. The individual forces in vector notation are denoted here. The forces on this 2m are in this direction, in this direction, in this direction. This is the 30-degree angle. Here as well it is 30 degrees. This angle is also 30 degrees. This is 60 degrees. No, wait, that's not 60 degrees. This angle is 90 degrees actually, but it's not needed right now. Okay, let's see. Solution. Three equal masses are placed at the three vertices of the triangle ABC. A mass 2m is placed at the centroid. Now, they're not, no, this is 1 meter is the mass, not mass, but it is a distance AG, and they gave the distance from the centroid. So we can easily find r square, which is 1 square, which is 1 actually. So first, the force FGA, that is the force at centroid due to A, that is towards the y-axis. So we take it along the y-axis. GM times 2m by 1 square in along the j vector, and this one is along the x-axis. No, wait, this is a resolution of the vectors here, but instead of that, it is better to take it as this angle is 120 degrees. Now taking the resultant of these two vectors, we will get a force in this direction, and this force should be around 2 times of the actual force since both magnitude is same. After using the triangular law of addition, vector addition, we will get the resultant force should be 2f, and this is f, so the force should be f downwards. From the principle of superposition and the law of vector additions, the resultant gravitational force, we will get it as 0. Wait, it's okay. This is the triangle. There are M, M masses placed at the vertices and 2m here, and F net should be, these are the direction of the forces. This is 120 degrees, and the resultant should be somewhere like this. As for the magnitude of the resultant, let's call it R magnitude, which is equals to both forces F, both magnitude are same, the direction is different. So F square plus F square plus 2 times of F into F cos 120 degree. Cos 120 degree, cos at second quadrant is negative. R the resultant magnitude 2F square plus 2F square cos of minus of sine 30 degrees, which is 2F square plus 2F square times minus 1 by 2, sine 30 is 1 by 2, 2 cancel, it will be 2F square minus F square So to cancel, we will get resultant, which is r vector, which is equals to root of f square, which is same as f. So resultant is equal to f. Then if we see in the diagram, this will be equal to f. This force will also be equal to f. Both are acting opposite to each other, so both will cancel out. F net, total force at the center, will be equal to 0 Newton. Now that's what they did here. Alternatively, one expects on the basis of symmetry that the resultant force ought to be 0. Now, if the mass at vertex A is doubled, they're saying that the force at the center, what will be the force at the center if the mass at vertex A is doubled? If this is 2m mass, then the force towards will also be doubled. So that must mean there will be a force 2f acting this time. 2f is acting upwards and f is acting downwards. Then this 2f minus f, since they are exactly opposite to each other, we will get the total net force acting f towards upward. 2gm square, that is basically f here, f which is equals to 2g, not 2 here, m, 2m by 1 square. This can be written as 2gm square. 2gm square, and it's acting along the j cap. This is basically f. For the gravitational force between an extended object like the Earth and a point mass, equation 7.5 is not directly applicable. Each point mass in the extended object will exert a force on the given point mass, and these forces will not all be in the same direction. We have to add up these forces vectorially for all the point masses in the extended object to get the total force. This is easily done by using calculus. Let's read that again. For gravitational force between extended object like the Earth and a point mass is not directly applicable. Equation 7.1 is not directly applicable. Each point mass in the extended object will exert a force on the given point mass, and these forces will not be in the same direction. They will have minute variation in the directions. We have to add up all these forces. Superposition theorem, like we saw, when there are 3 to 4, we add them vectorially. Similarly here, it will be many particles, thousands of particles. Here also we should hundreds of thousands of particles. Here also we should add them vectorially, considering each of the direction force in each direction. We have to add up these forces vectorially for all point masses in the extended object to get the total force, and this can be easily done using calculus. For two special cases, a simple law results when you do that. The forces of attraction between a hollow spherical shell of a uniform density and a point mass situated outside is just as if the entire mass of the shell is concentrated at the center of the cell. Okay, when we consider attraction between a hollow spherical shell, it is having a uniform density. Shell meaning it's just a ball. It's hollow, there is nothing inside, but it is having mass due to the outer surface. And between this shell and a point mass situated outside it, the force of attraction is just like, even though this is not a point, even though it's not a point mass, but still the force of attraction between this interaction is similar as if this hollow spherical shell was a point mass. It's as if all its mass was concentrated at the center. Qualitatively, this can be understood as follows. Gravitational forces caused by various regions have the shell of the shell have components along the line joining the point to the mass center as well as along a direction perpendicular to this line. The components perpendicular to this line cancel out when summing over all regions and the shell leaving on a resultant force along the line joining the point to the center. The magnitude of this force works out to be as stated above. Even though it's not a point mass, because of the addition of vectors where perpendicular ones which are opposite to each other get cancelled out, because of that it will be acting or like we will get the value if we consider it even as a point mass. We will get the exact correct value even if we consider the shell as a point mass. The second law is the force of attraction due to a hollow spherical shell of uniform density on a point mass situated inside it is zero. The force of attraction due to a hollow spherical shell of uniform density. Okay, we are considering force of attraction due to a hollow spherical shell of. Okay, this is we are considering the same kind of shell, and what the law states is that if we consider a shell, the same kind of shell, uniform density, it's hollow inside. And if we put a uniform mass inside it, it's a point mass. This is separate to the shell. There is already a, let's see it in word. If there is a shell, this is a circular shell. It seems like an oval, but it's a circular shell. This is a circular shell. It's hollow. And if we place a point mass, this is a point mass, mass 2, this is mass 1, and we are placing a mass 2 inside this uh, spherical shell or a hollow shell. Then the force experienced by this mass m2, force on m2 due to m1 will be 0. Why this is because when this point at this let's assume at this is a point particle in the whole shell m1, it is this, due to this the force of attraction will be this side, and somewhere here another particle will show a force of attraction this side. These both will get cancelled out. Because of that, the total force experienced at any point inside this spherical shell will be 0. That is what the law states. Qualitatively, we can again understand this result. Various regions of the spherical shell attract the point mass inside it in various directions. These forces cancel each other completely. Now let's go to the next main topic, that is the gravitational constant. The value of gravitational constant G, the universal gravitational constant, is represented by the capital letter G. It has a constant value. The value of the gravitational constant G entering the universal law of gravitation can be determined experimentally, and this was first done by English scientist Henry Cavendish in 1798. The apparatus used by him is schematically shown in 7.6. This is the experiment schematic drawing of Cavendish's experiment. S1 and S2 are large spheres which are kept on either side, shown shades of the masses, or they have masses A and B. When the big spheres are taken to the other side of the masses, shown as dotted circles, the bar AB rotates a little since the torque reverses direction. The angle of rotation can be measured experimentally. Okay, S1 here, S2, they are large spheres, the shaded ones, and they are kept on either side, and they have masses A and B. Now they are kept at points at A and B. They are kept at points A and B, and when these big spheres are taken to the other side, this first kept here and here, but they are taken again to here and here. When that happens, the bar AB rotates since the torque direction reverses. This angle, how much angle they rotated, can be measured experimentally. There seems to be an error. Okay. Okay, it's more explained here. More explanation is given here. The bar AB has two small lead spheres attached at its ends. The bar is suspended from a rigid support by a fine wire. Two large lead spheres are brought close to the small ones, but on opposite sides as shown. The big spheres attract the nearby small ones by equal and opposite force as shown. There is no net force on the bar, but only a torque which is clearly equal to F times the length of the bar, where F is the force of attraction between a big sphere and its neighboring small sphere. Due to this torque, the suspended wire gets twisted till such time as the restoring torque of the wire equals the gravitational torque. If theta is the angle of twist of the suspender wire, the restoring torque is proportional to theta, equal to tau theta, where tau is the restoring couple per angle of twist. Tau can be measured independently, example by applying a known torque and measuring the angle of twist. The gravitational force between the spherical balls is the same as if their masses are concentrated at their centers. Thus, if D is the separation between the centers of the big and its neighboring small ball M, and M their masses, the gravitational force between the big sphere and its neighboring small ball is F equals GMM D square. If L is the length of the bar AB, then the torque arising out of F is multiplied by L. At equilibrium, this is equal to the restoring torque, and hence, if L is the length of, then torque arising out of F is F multiplied by L. At equilibrium, when it's not at rest, when the net force is 0, the restoring torque, this will be equal to the restoring torque. This is force times L, which is equal to tau times theta. Observation of theta thus enables one to calculate G from this equation. Since Cavendish's experiment, the measurement of G has been refined and the currently accepted value is 6.67 into 10 power minus 11 Newton meter square per kg. Basically, he took a rigid support, he took a wire, he took a rod and attached at the center of the rod. The wire was attached to the center of the rod, and he kept two hard spears at the ends of the rod, and at the sides of these two rods he kept small spears. And due to attraction between the large spear and a small spear, there will be a torque in the system, because of which there will be turning of the total system. This total will get continue to spin. This will go this side, and this will come this side, and this is measured. The angle is measured when in equilibrium. It is equated to tau theta, and we'll get G value. The current accepted value is 6.67 into 10 power minus 11. Okay, then I'll continue it later.